Newton's third law of motion. For every action there is an equal and opposite reaction. So when two objects interact, they exert forces on each other which are equal in magnitude but opposite in direction. So for instance, I have a 10 kilogram block which when placed on a table exerts a force equal to its weight on the table. So that's a 98 Newton force acting vertically downwards. Now the table will resist the block by exerting a force on the block that's equal to 98 newtons, but in the opposite direction. This is the reaction force. Action, reaction, same magnitude, and the arrows tell you that the forces are in opposite directions. Remember, forces are vectors. They have magnitude and direction given by arrows on diagrams. Example 1. So we have a rough surface with two blocks, 3 kilograms and 5 kilograms, and if we look at their normal reaction forces, we can see that R1 is equal to 3g and R2 is equal to 5g. There's no acceleration vertically, the forces are balanced, so we're going to ignore these forces. Okay, so back to the blocks. They are connected by a rope and the rope is tight. This person pulls on the 5 kilogram block with a 40 Newton force. The 5 kilogram block is attached via a tight rope to this 3 kilogram block. As the person pulls, the rope is tight and there is a tension force in the rope. Now the rope is pulling on this block, so the tension is in this direction for the 3 kilogram block. The 3 kilogram block is pulling on the 5 kilogram block, so the tension here is in the opposite direction. So we have this, and you can see T is the same magnitude here and here, but these forces are in opposite directions. Now the surface on which these blocks are standing is rough, which means we need to consider friction. Friction always opposes motion, so frictional forces are in the opposite direction to motion. So we can see here that the 3 kilogram block has a frictional force of 6 newtons, and that's not something that we've calculated in the problem that was given. Likewise, the 5 kilogram block experiences a 10 Newton frictional force, and both of these in red represent friction, and they are both in the opposite direction to motion. So there will be a resultant force towards the right, which will lead to an acceleration towards the right. So for problem solving, I will take this direction as positive. So we have to work out T, the magnitude of the tension in the rope, and we have to work out the acceleration of the system A. So just considering this block, if we do F equals ma, so 40 minus 10 minus T, that's the resultant force, equals the mass 5 times acceleration. So we get this equation here. Now we'll consider the other half of the system here. So T minus 6, which is the resultant force, is equal to mass times acceleration A. Now T is the same for both systems, so for this system and this part here, and the acceleration is the same here and here as well, because the rope was tight. So now we have some simultaneous equations to solve here. So if we just add them together, we get A equals 3 meters per second squared and T equals 15 newtons. Now we can connect our two systems together and pretend there's a single block of mass 8 kilograms. Yeah, this comes under the connected particles topic. So we still have a 40 Newton force applied here by this person. There's no rope anymore, so there's no T, the tension in a string or a rope to consider. There are the two frictional forces, they are still present. So F resultant equals ma, so 40 minus 10 minus 6 equals the mass the combined mass times the acceleration, and again we can work out what the acceleration is, 3 meters per second squared, exactly the same as before, but there's no T, the tension in the rope to work out this time. Okay, so we have a crane, we can put a weight here, and there will be some kind of tension in this rope here. So we're going to look at just this part of the system. Okay, so here's the balance, and here was the rope, and there's some tension in there, and we've got some masses here, 400 gram mass, or 0.4 kilograms and 0.6 kilograms. Yeah, we should be working in kilograms and not grams. So their respective weights, and weight is a force. We're given that the acceleration of the whole system is upwards at 0.5 meters per second squared. And because acceleration is upwards, I'm taking the upwards direction as positive. We're trying to work out T, the tension in the string, so F equals ma. This is the second law. We'll use it because we have acceleration. So we have T minus 0.4g minus 0.6g, so that's the resultant force, equals mass, so we've got these two masses to add together, times acceleration, and we know what g is, 9.8 meters per second squared, so T is equal to 10.3 newtons. Okay, part B, what's the force exerted on the 600 gram mass by the 400 gram mass? It's this force here, represented by R, and we need to know if there's any acceleration in the system before we can answer this question. So we're going to consider two scenarios here, and the first one, that there is no acceleration. If there's no acceleration, we don't need to use the second law, we can use Newton's first law. So the resultant force will be 0 because the forces are in equilibrium, they're balanced. So R is equal to 0.4 g upward forces equal downward forces. Essentially this is what it is. So G is 9.8, so R is equal to 3.92 newtons. So remember, by the third law, the 400 gram mass here pushes down on the 600 gram mass, and the 600 gram mass is pushing upwards on the 400 gram mass by an equal and opposite force, equal in magnitude but opposite in direction. Okay, so same again, but this time we have acceleration, 0.5 meters per second squared upwards. So now we can't use the first law, we're going to use Newton's second law, F equals ma. So the resultant force, and if I'm taking this direction as positive, will be R minus 0.4 g equals the mass, because I'm focusing on the 400 gram mass here, times the acceleration. So R minus 0.4 g equals the mass, the 400 gram mass, times the acceleration, and we have R is equal to 4.1 newtons. So the 400 gram mass is pushing down on the 600 gram mass with a force of magnitude 4.1 newtons, and the 600 gram mass is pushing upwards on the 400 gram mass with a force of 4.1 newtons. It's the same force but in opposite directions. It's the third law, the equal and opposite force. So extending the same concept a little bit further, what's the force exerted on the 600 gram mass by the balance? Now the balance has got no idea whether it's just a single 1 kilogram mass sitting on top of it, or whether there are two separate masses of 600 and 400 grams sitting on top. So we can combine these two masses together into a 1 kilogram mass. But again, we need to know if there's any acceleration, and we're going to look at two scenarios like before. Okay, so here the acceleration is 0, so we can use Newton's first law, so the resultant force will be 0. So R, the normal reaction, equal to 1g. It's 1 kilogram altogether times g, so just 9.8 newtons. And the second scenario where there is acceleration, so we can use Newton's second law this time. So now we have F equals ma, so the resultant force will be R minus 1g equals mass, 1 kilogram, times the acceleration, 0.5, and we can solve to get R, 10.3 newtons. For practice, try these questions.